Hi, I'm Jianan Yao, and I'm here to present the joint work with my collaborators at Columbia University, Gabriel Ryan and Justin Wong, advised by Suman Jana and Runhui Gu. We introduced gated continuous logic networks, GCLN, a neural architecture for inferring loop invariants. In critical applications, formal verification rigorously guarantees that these programs are bug-free. This ensures that the software operates correctly when it is deployed. Most aspects of formal verification can be performed automatically. However, loops require additional information. In particular, verifying a loop requires identifying a loop invariant, which concisely captures the behavior of the loop. Once a loop invariant is provided, the correctness of the program can be automatically checked. This identification process is often done manually by an expert and is usually difficult and time-consuming. Our work addresses this key challenge of automation. Given a loop invariant is a logical formula that holds before the loop executes, that is to say, it can be derived from the precondition. During execution, it holds true from one iteration to the next, and after the loop terminates, that it suffices to prove the desired postcondition. As the invariant can be any arbitrary logical formula, loop invariant inference is undecidable in general and remains an open problem in practice. Automatically inferring the invariant becomes even more difficult when it requires nonlinear terms, which is our focus in this work. Loops for many common numerical operations require nonlinear invariants. As an example, consider this loop which efficiently computes the cube of A. This simple loop requires an invariant with a conjunction of four constraints, including a third-order polynomial constraint, that is, x equal to n cubed. We provide an overview of our approach to nonlinear loop invariant inference, starting from this loop as input. We first instrument the source code and record a trace of the program variables during execution. We take a data-driven approach to loop invariant inference, so these serve as the primary input to our system. We record the values of all program variables at the beginning of each iteration, and by default, we expand all monomial terms up to a given degree. That is how we get this table of samples. We next use the data to train a model to learn a candidate invariant. Finally, once the invariant is learned, the candidate is verified by an SMT solver such as Z3. The key question our work addresses is, how can we most effectively learn a nonlinear loop invariant given its execution traces? We know that the invariant here is a logical formula, and all these samples from the execution traces satisfy this formula. In other words, the question is, how to learn a logical formula f from samples that satisfy f. We base our approach to nonlinear loop invariant inference on continuous logic networks, or CLNs, a neural network architecture from prior work designed for learning linear SMT formulas directly from data. Given the structure of the formula, CLN can learn the weights, or the parameters, here W0, W1, W2, and W3, from the samples that satisfy the formula F. CLNs use a parametric relaxation of SMT formulas to convert them into smooth and differentiable functions. Consider this formula f, which is either true or false, for various values of x. Deep learning doesn't work for f, since f is now a discrete function. To make deep learning possible, CLNs propose a relaxation, shown as the red dashed line, which closely approximates the behavior of the discrete SMT formula. Since now it's a continuous function, it can be used with gradient descent. This relaxation uses functions called T-norms and T-conorms to model logical ANDs and ORs. Here we use a product T-norm in our work, which defines the T-norm as a product of the inputs. You can check this is reasonable because P times Q only reaches 1 when both P and Q are 1. This is what we want for a logical AND, but now it's a continuous function of P and Q. Similarly, we use the product T-conorm defined as the sum of their inputs minus their product. Equality and inequality constraints are defined in the relaxation using modified sigmoid and Gaussian functions. The formal definitions can be found in the paper. For inequality, when x minus b is very large, the truth value of x greater than b, or x greater than or equal to b, will be close to 1. For equality, when x is close to 0, the truth value of x equal to 0 is close to 1. When combined with T-norms and T-conorms, an SMT formula can be relaxed into a continuous and differentiable function. Then, we can use gradient descent to learn the parameters in the formula. When inferring nonlinear loop invariants, we face 3 major challenges. We will discuss how we address each of these challenges. First, to effectively search over the space of nonlinear loop invariants, we introduce 2 new constructions to the CLN architecture, gating and dropout. If you are familiar with deep learning, gating and dropout are common practice there, but our gating and dropout are different, and they are specialized for learning logical formulas from data with CLNs. We introduce a notion of gated T-norm. Intuitively, these gates can turn the associated input on and off. Gated T-norm is formally defined here, with additional gating parameters G1 and G2, which are learned during model training. The gated T-norm defined this way has the following property. You can see that when both G1 and G2 are 1, it becomes a normal T-norm. When G1 is 0, input X is ignored. When G2 is 0, input Y is ignored. So G1, G2 are gates, which determines whether input X or Y is activated, and they are learnable parameters between 0 and 1. We also have a parallel construction for gated T-conorms, which can be found in our paper. Here in this example, the gated T-norms allow us to ignore the third equality. If the model converges to this, which basically means that the third equality doesn't fit the samples and its gate is turned off during training, then the final formula learned will be this: a conjunction of the last clause with the disjunction of the first 2 clauses. We next discuss term dropout. In nonlinear loop invariant learning, there is an exponential number of possible terms, making model learning difficult. To address this, we introduce term dropout. Term dropout works similarly to dropout in standard neural architectures, but is fixed at the beginning of training. Term dropout operates by imposing a random mask on the terms. For example, here the terms x, xy, and x squared z are excluded by the mask. Then the model will only learn a relation between the other 4 terms. Different random masks are used for each neuron in the network. Later, they are combined to get a complete formula. We next discuss how we construct a new activation function, the piecewise biased quadratic unit, or PBQU, to learn tight inequality constraints. When learning inequality constraints from a set of program samples, there are many possible valid constraints. For example, consider the 2 inequality constraints learned from samples of the SQRT program, shown as dotted lines. Both of these are valid loop invariants that are maintained by the loop. However, neither is sufficient to prove the postcondition, a squared smaller than or equal to n. In order to prove the postcondition for this program, the invariant must constrain the samples as tightly as possible. In this case, the necessary inequality constraint is a squared smaller than or equal to n. To learn tight inequality constraints, we replace the sigmoid activation with a new activation function, the piecewise biased quadratic unit, or PBQU. The PBQU is shaped to output the highest possible value when it fits an inequality constraint as tightly as possible. This means that it naturally converges to tightest possible constraint during training. We discussed the construction of PBQU in more detail in our paper. Now we look at the last challenge. In some cases, the number or the quality of the training samples are limited due to program constraints, so we introduce fractional sampling to generate more samples. Here we show the samples from running the program normally. We can see that just as a fourth iteration, the term xy is much larger than all other terms. This makes model learning very difficult. From the machine learning perspective, we hope to have more samples from other initial states. For example, here we show the samples if we run the program from n is 0, x is 0.5, y is minus 1.5, and z is 2.4. However, this contradicts the precondition of the loop and leads to unsound invariants. Our solution is to learn a more general invariant, an invariant that holds for all initial states. The loop invariant can be considered a predicate over program variables v, initialized with v0. The normal definition of the loop invariant says that if after some iterations we reach the state v, then v must satisfy the loop invariant I. Instead, we try to learn a more general invariant I', such that for any initial state vi, if after some iterations we reach the state v, then vi and v combined must satisfy the loop invariant I'. If this is possible, and then if we assign the real initial state v0 to vi, then we get the exact loop invariant that we need. Note that a more general invariant is not always feasible. In the paper, we discuss more details. To recap, we addressed the large space of nonlinear loop invariants, necessity for learning tight inequalities, and limited samples from programs with four methods: logic states, term dropout, the PBQU activation, and fractional sampling. We combine these methods in the gated continuous logic networks, or GCLN architecture, which can then learn invariants end-to-end using gradient descent. Using this neural architecture, we built an invariant inference engine which generates samples to send to GCLN and then checks the candidate invariant using the Z3 SMT solver. Our method solves 26 of 27 problems in the NLA polynomial invariant benchmark, an improvement by 3 from the previous state-of-the-art. Further, it is efficient, requiring only 53 seconds to run. We also evaluate it on the code-to-M linear invariant benchmark, which we are able to solve all 124 problems in less than 30 seconds per problem. In summary, we introduced a new neural architecture for efficiently learning nonlinear loop invariants. For more details, see our paper and our source code on GitHub. We are happy to answer any questions, and we want to thank you for taking the time to listen.